Hey everyone, welcome back to another video by Camroom 5. In today's video, we're going to continue transition elements and we'll talk about the shape of the 3D orbitals. Because we'll need this understanding to understand the concept of complex formation which transition elements do. So imagine the three axes, X, Y, and Z. You also need to imagine the planes between these axes. Like for example, the blue one is the XZ plane between the X and Z axis. Now you can imagine the pink plane which is between the Y and Z axis, so it's the YZ plane. And then there's this green plane between the X and Y axis. These flat sheets represent the planes between these axes. The first set of d orbitals is present not on the axis but between the axes. For example, the 3D YZ orbitals has 4 lobes in total. So the DYZ orbital has 4 lobes in total, and these 4 lobes are present between the Y and Z axis. So it is present on the quadrants, not on the axis. So it is present on the YZ plane between the Y and Z axis. Let's imagine the 3D XZ orbital, which is present as 4 lobes. It is present as 4 lobes between the X and Z axis. So it's present not on the axis, but it's present between the X and Z axis. And you can also say it is present on the XZ plane, the blue one. Then now you can imagine the 3D XY set of orbital, which has again 4 lobes in this orbital, and these 4 lobes are present between the X and Y axes. Or you can also say it is present on the XY plane. The other 2 orbitals are present on the axis. Now you can imagine, now you can see the 3D x square y square. The way we write is x square hyphen y square. It also has 4 lobes, but these are present on the axis, not between. It is present on the X and Y axis. It is not present between the axes. The last orbital, the most interesting one, is the 3D Z square orbital, which is present on the Z axis alone. It has only 2 lobes and it has a circular ring like a donut in between the lobes, and these 2 lobes are present on the Z axis. So between the axis orbitals and on the axis orbitals, these are the total 5 orbitals. Let's use this understanding to create the ideas about complex formation. We need to imagine iron to start our understanding. Let's imagine iron with its electronic configuration, which ends with 4s2 3d6. If you were to imagine these orbitals as circular spots, just for understanding, to put them on a graph, you will be able to see that the energy levels of these subshells and orbitals increase gradually. We have 4s, then we have 3d with 5 orbitals, and then we have 4p with 3 orbitals. 4p is entirely vacant, but it's hypothetically there. When I fill the electrons, you can see this is how they would be filled. 4p will be entirely vacant, but if I'm talking about iron atom, that's okay. What about iron plus 2 ion? For iron plus 2 ion, the 2 electrons from the 4s subshell will be lost. The 4s2 will be 0, so I should remove the electrons from the 4s subshell. So 4s is vacant now. 4s subshell has no electrons because they have been lost while iron became plus 2 ion. So 4s is vacant, 4p was already vacant. 3d makes sure to pair up the electrons so that even 2 orbitals from 3d are vacant. There are overall 6 vacant orbitals. 4s is vacant, the 2 orbitals of 3d are vacant, and the 3 orbitals of 4p are vacant. These are the vacant orbitals with no electrons in them at all. These orbitals can accept electron pairs and make coordinate covalent bond. Let's imagine the same axis and let's put iron plus 2 ion in the center. The 3D with 2 orbitals, the 4s and the 4p orbitals were vacant, right? So we had 3 4p's, 2 3d's and a single 4s. So 6 vacant orbitals. These vacant orbitals allow any lone pair donor, for example water or anything, to give their lone pairs to the atom, or sorry, I should have said to the ion, and make coordinate covalent bond or dative bond. You can see I am drawing 6 water molecules which are going to be working as lone pair donors and make 6 dative bonds with my iron plus 2 ion. Here water is acting as a lone pair donor. You can also call it the phrase, which is new for us, ligand. It makes a coordinate bond, and in terms of transition element chemistry, we call such species as ligands. So it makes a coordinate bond with my transition metal ion and it's called a ligand. Ligand. Ligand is a lone pair donor, or you can say Lewis base. The shape of the complex will include one water ligand on top, one water ligand at the bottom, and the other 4 ligands on the corners of a square, and that is the shape known as the octahedral shape, where there is 90-degree angle between all these coordinate covalent bonds. So the geometry of this overall complex is octahedral. I will put square bracket around this entire complex and I will write +2 charge because water never had a charge on it, but iron was a +2 ion. So due to the metal ion, the overall complex is still +2. The formula can be written as Fe, H2O inside a bracket, then 6, and then square brackets to show the complex. The 6 means that there are 6 water ligands, or you can say 6 coordinate bonds made by each water ligand. 1 coordinate bond by each ligand and then overall 6 bonds. The water is the ligand here, which is donating the lone pair, and iron is obviously my transition metal ion. In this case, each ligand makes 1 coordinate bond each by donating a lone pair. In order to just solidify our understanding more, we should write the definition of the phrase ligand. A ligand is a chemical species. It can be atom, it can be ion, it can be a molecule. So it's a chemical species that makes a coordinate covalent bond, or you can say coordinate bond, by donating a lone pair or more lone pairs to a transition metal ion or metal atom. It could be either of those. We need to talk about the ligand classification so that in the upcoming videos we are well prepared with this. So they are classified on the basis of the bonds they make, like for example how many coordinate bonds and the charge they have. We have the phrase monodentate. Mono means 1, dentate means how many coordinate bonds. So monodentate are the ligands that make 1 coordinate bond by donating 1 lone pair only. For example, chloride ion, which makes 1 coordinate bond, bromide ion, iodide ion, hydroxide ion. Then we have more examples. For example, water, like our example. Ammonia has 1 lone pair donor, which is nitrogen atom. Cyanide ion, which makes 1 dative bond each. Then we have thiocyanate, which is SCN, where sulfur gives the lone pair. We have carbonyl, so that's also a kind of monodentate ligand. Then we have some bidentate ligands. Bi means 2, dentate means how many coordinate bonds you make. So they make 2 coordinate bonds with the ligand, obviously. These definitions will be good for you when we do P4 practice. The most common example is ethylene diamine. It is also written as small en, like short case, small en. This is the structure of ethylene diamine when there are two carbon atoms in middle and there are two imine groups on, like one imine group on either side. Then we have oxalate or ethane dioate, which is another bidentate ligand. It has two carboxylate groups joined together. The oxygens with the negative charge, one oxygen on either side, has lone pairs, and these two oxygen atoms in the molecule are the lone pair donors. Then we have polydentate ligands. Poly means more, and then dentate means, again, bonds, coordinate bonds. So they make more than two coordinate bonds with the transition metal atom or the transition metal ion. One of the most common examples we have is ethylene triamine, where we have three imine groups, one in the middle, one on either side, and then two ethylene groups. Ethylene means two carbon groups. There are three nitrogen atoms. All three have one lone pair each, and these three nitrogen atoms act as ligands, so they can make three coordinate bonds at the same time. Another example, let's write the name of this word, diethylene triamine, because it has two ethylene groups and it has three amine groups. You can see overall it can make three dative bonds at the same time. Then we have ethylene diamine tetraacetate group. This is also known as capital ADTA, which has a charge of -4. The structure is very complicated, but it's very good that you have an understanding of how this happens. It has ethylene, like a carbon pair in the middle, and then it has two nitrogens, each having two acetate groups. So there are overall 6 atoms you can see in this diagram which make one coordinate bond each. So ADTA can make 6 coordinate bonds at the freaking same time. So it's hexadentate ligand. On the basis of charge, you have some of the ligands which are negatively charged, like chloride, bromide, iodide, hydroxide. Sulfate is like -2. Cyanide, Cn is -1. Oxalato, which means like the oxalate ethane dioate, has -2 charge on it. ADTA has -4 charge on it. So these are all negative ligands. Then we have some neutral ligands. For example, carbonyl is neutral. Ammonia is for sure neutral. Water is neutral. Then we have ethylene diamine, which is small e, small n, which is neutral.